End-to-End Encrypted Audio Calls by Emad Heydari Beni. Welcome, Emad.
Thank you for the introduction. My name is Emad. This is the joint work with my colleagues at Nokia. You might remember us from this rock-solid product, if you're old enough. I think there are a lot of old people here. But today, we are building infrastructure that powers the internet. For example, we are building network routers that can process up to 400 terabits per second. We are also one of the leaders in building and deploying infrastructure for 6G and 5G network, future 6G. We don't have 6G yet. Okay. In 2021, there was this funny situation in which a senior lawyer had this cat filter on. You might have seen this. What would you do if you were in such a call, if you were him? I would switch off the camera and continue the call. But what if the audio was not working and the video was fine? I think we couldn't have the call, right? We would cancel the call. So audio is really important in such a calls and sessions that are sensitive or not sensitive even. For many years, we have been building systems and protocols for end-to-end encryption. We have many protocols like Signal Protocol and also the MLS standardization. But we didn't talk enough and we didn't care enough about audio from security and privacy and also efficiency perspective. So in this talk, I want to share our results with you from this perspective. If you take your phone and go to the operator setting, there's an option called Voice over LTE. So when you when you call someone, your audio signal goes through an infrastructure known as IMS. IMS is standardized by 3GPP. So your audio signal is encrypted, sent to an operator server. The operator server decrypts it. They enhance the audio. They do some operations on it. They encrypt it again and send it to the recipient. This can be more complex if the recipient comes from a different operator. So the operator server sends to the other operator, they decrypt it, they enhance the audio or do other processing, and they send it to the recipient. This could be even more complex. It can be a conference call. If there are multiple people talking from the same, multiple people are in a call. And if these two people talk at the same time, or if they don't talk even, the audio signal goes to the focus server from their operator, and the audio signal is combined into one stream to optimize the network. And then that mixed stream is transferred and relayed to the next operator server and sent to the recipients, and they can have a call. So this process is called audio mixing. So if I want to generalize audio mixing, Alice talks with microphone. Microphone captures the audio signal. The audio signal is transferred to the other participants, and the others also in a call, they're talking, the audio signal is captured and sent to everyone else. But as you can see, the network traffic is not nice. It grows quadratically. But we can do better, like IMS. We could send it to a central server, and the central server would mix it centrally and send back the mixed stream to everyone else. And we would have linear network traffic, and it's much better. But if you want to have end-to-end encryption, this would not work because audio mixing happens in plain text domain. So we have to have the plain text signal to be able to do the mixing. So this is hard. We are back to square one. Again, if we want to have end-to-end encryption, we have to encrypt the signal and send it to everyone else. And then locally, each participant performs audio mixing and they can play it back. But we would like to have end-to-end encryption, but this is not good because traffic grows quadratically, as I said before. And also audio synchronization is harder because we don't have central server. So that means we don't have central clock that we can use for synchronization. And now we have to deal with the distributed systems, which is really harder to have high quality audio call. And also some of these enhancing techniques for audio are proprietary, and companies, they're reluctant to ship this to the client side. We cannot also perform all of those nice proprietary audio enhancement technologies. You might say, I've been in big meetings that everyone else is muted and one guy is talking. And he talks, you can have end-to-end encryption, easily, and then there is no network traffic. But we know who's talking, so there is no speaker anonymity. So we would like to build infrastructure for everyone that at least we can preserve this quality. We can have a speaker anonymity. So this is not something, having no speaker anonymity is not something that we would like to have. But so in an ideal world, it would be really nice to have end-to-end encryption and have some server, central server there that can obliviously mix the audio stream and send it back to every participant. But in plain text domain, without having a decryption key. So we are in real world crypto. We have to see how we can achieve that. So we looked into the literature to see whether there is any previous attempt to fix this, to solve this problem. We found this paper from many years ago that they use homomorphic encryption to encrypt the audio and also mix it centrally. We found this very interesting, and also there's a thesis that tried different schemes with homomorphic encryption and and presented some benchmarks. We thought, okay, let's call this blind audio mixing. That means every participant in a call encrypts the signal, send it to the central server. The central server performs SIMD addition and send back the mix to every participant. But there's a caveat here. In homomorphic encryption, if you take the plain text audio and you encrypt it, you will have expansion. For very small parameters, you can easily have 10x expansion. And if you want to really do more processing on the audio and have more noise room, if you're familiar with FHE, then this number can be easily 30x or 40x. And audio is not forgiving. Real-time audio is not forgiving, because if you want to have high-quality real-time audio, the maximum latency should be at least less than half a second, as you can see. And also, the maximum bandwidth consumption should be less than 1 megabit per second, which is already a lot. But with this setting, this is not going to happen. We thought we can play with the FHE parameters, but then there is a limit. We cannot get smaller and smaller. So we thought let's compress the plain text signal before encryption. So we compress the audio signal. For compression, you can imagine something like, for example, MP3. And then let's encrypt it, add it with FHE, then decrypt it, then what we get is garbage. Because, yeah, that's fact. Because if you use MP3, the homomorphism of the plain text data for audio mixing, because audio mixing basically is addition of the signal, if you're familiar with audio, this does not work. We thought, okay, let's decompress, then evaluate. We encrypt the audio signal, we compress the audio signal, like before, we encrypt it. In the encrypted domain, we run the decompression circuit with FHE. Then we add it, we decrypt it, and we have the mix. In fact, it works. But we want to be real time. This is not going to work. If you want to compute the FHE circuit of decompression, it's going to be very slow. Maybe with hardware accelerators one day, but we're not there yet. We thought, again, we have to go to the ideal world land. What we want, we would like to have an additive homomorphic compression. You might have seen this paper from Google more than 10 years ago, if I'm right, which is known as Word2Vec, which is about text embeddings. What are embeddings in neural network? Embeddings are vectors of features. Then you feed some data in it. So what they have done, they feed text data to this neural network and they got embeddings. And they observe that linear operations like addition, subtraction, if you have perform these operations on these embeddings, you are again receiving a new embedding which has a meaning in that domain, in the latent space. For example, if you have Paris minus France plus Bulgaria, you would get embedding of Sofia, which is very interesting discovery. We thought, can audio embedding have some homomorphism? We thought, let's try this. But there is also a famous hypothesis, which is known as linear representation hypothesis in the AI community, which states that an embedding is a linear combination of features, F. And if you have two embeddings, if you add them together, you get a new embedding, which is a valid embedding, and it is also, again, a linear combination of features. So there is some notion of homomorphism there, additive, especially additive and additive homomorphism. We thought, let's put this in practice and see what happens. Then we thought we need a neural compressor. neural audio compressor. We found this paper. Shout out to people at Meta for writing this fantastic paper and also providing the source code for us, for everyone, and the model and everything. We took this paper. Well, maybe first explain how the paper works. You take the audio signal, the raw audio signal, give it to this block, which is an encoder, which is composed of a number of convolutional layers. As you can see, the width of convolutions is getting tighter and tighter. So that compresses the audio. And what you get after the encoder is a vector of vectors. Vector is the number of embeddings that are representing this audio. Then there's the quantization layer in between. What it does is that quantization, if you're familiar, there are code books of lots of different embeddings. And what it does, it checks that if your vector of features close to certain vector in the code book, they take that index and replace the audio signal with that index. So we would end up with a bunch of indices which represent your audio when we're compressing. Then we thought indexes are not going to be additive homomorphic. You have to drop this part. We take the embeddings from the output of the first block, which is already compressed in time domain and also in amplitude. We take this, and we thought, okay, let's put this in practice to see what happens. We fit the audio signal to the encoder, and we get some embeddings. Then we can even truncate it more because it's audio signal to have a smaller, in this example, 8-bit values. And then we encrypt this. We add this homomorphically. We decrypt it. We do the decoder with a reverse process, and we get the audio. We discovered that audio embeddings have additive homomorphism, and we can have audio mixing with this, meaning that if you're talking, if I'm talking, and we have two signals, if you add them, the final signal you get here is like both of us talking at the same time, which is really cool. But this is even more interesting because we can do more configurations. There's a degree of customizability here because, as you can see, there's a width of the convolutions there, the blue boxes. You can have different size for different width for each block. So that means that we're flexible to have different degree of compression, different rate of embeddings per second, and we can also truncate to different sizes. We can have different number of bits, and that allows us to optimize towards different network environments. For example, we can have low bandwidth, optimize towards low bandwidth settings or low latency settings, or even different quality of audio. And this gives us real-time and flexible, and of course, obviously, secure streams if you combine it with the homomorphic encryption. We thought, okay, let's implement this and see what are the numbers, because we want to see, can we be real-time or not? If you see in the blue line is the mesh architecture that we had, the mesh setting. But this is network load per user, like how many megabits per second per user. So the blue line is the consumption, is the mesh setting. So everyone is sending audio signals to each other. You can see with more number of users, we are consuming, this is going up rapidly. This is not good. And the purple one, do I have a pointer here? Okay, it doesn't matter. The purple one, that one is end-to-end encryption without any compression. As you can see, this is not more than 5 megabits per second. It's not going to be real time, or the bandwidth is really bad. But the green one is with the compression. As you can see, this is like end-to-end encrypted centrally with compression, and this is almost less than 1 megabit per second. So we can have real-time audio call. And this is really fantastic result for me. But the overall network load is also like that. As you can see, the blue one, which was the mesh, it grows quadratically with more number of users. But what we have to look at here is the green one. Green one is us, and the red is plain text with no end-to-end encryption. Nothing, just IMS, central server. We are almost very close to that one, which is very good. But there are a lot of open challenges. The story is not over. I mean, this is just the first result we have in this domain. So we are real time, but if we want to perform more advanced audio processing, like, I don't know, some advanced processing, it is likely that we cannot be real time. So we need more innovation there in terms of hardware acceleration. And there are some companies working on this. I hope we can have hardware acceleration as soon as possible. But also, we optimize the bandwidth. We can still get better, I'm sure. For example, we can have better deciphering schemes, faster, hardware accelerated. We need more innovations there. We are not there yet. And also, we as Nokia, we are in a situation, we are in a position that we can incorporate FHE in different spec. But as long as it is not standardized, it is not easy to do that. So there is a standardization committee, and there was a meeting, I think, before this conference. We look forward to seeing this getting standardized that we can use it in real world. But we focus so far on the bandwidth and the architecture, homomorphic encryption, and that aspect. But of course, we need group key management, something like MLS. But this is slightly different. We have different requirements because keys in homomorphic encryption, if you are familiar, there are different keys, and we are not dealing with 40 bytes. We are dealing with hundreds of megabytes or sometimes gigabytes of keys. So requirements are slightly different. This is open. We haven't looked into that. We're going to look into that, and I hope we can collaborate with some of you to make this work. And last but not least, in every country almost in the world, I checked on Wikipedia, there is a law about lawful interception. We have been building apps like Signal, like, I don't know, other platforms that are end-to-end encryption, but we don't care about infrastructure that much. And it's 2025. I think we have to find a solution for this as a community. Just wanted to raise this. Yeah. We have a demo. If you want to see this working, we build a prototype. You can come after the talk with me and my colleague Lode, who's sitting here. We can show you that actually this works, and we can try it together. Thank you.
So if I understood right, you are just doing linearly homomorphic encryption. You're just adding stuff, yeah?
Yeah.
So why not just throw out CKKS and BFE and whatever and just use Paleo? Because then your bandwidth expansion is going to be really, really small.
Yeah, but
it's not as cool.
That's true. It's not cool. It's not post-quantum. But first, we want to be post-quantum, but that's one reason. The second reason is that with CKKS, we can batch lots of samples. Audio signals are a lot.
Oh, I see. So you could do a lot.
Yeah.
Okay.
That's why I dropped the SIMD term there for those that didn't know what I mean. Because there are a lot of samples. Boom.
So a lot of the overhead here might be due to the assumption that you need to be able to add the signals from N streams rather than, say, the 3 loudest streams. Is it possible to say, so you have N encrypted streams, but in the FHE scheme or whatever simpler scheme you use, you detect the 3 loudest ones and produce an encrypted version of that? Is that an easier problem than trying to add all of them?
I'm not sure I understand the question. Could you repeat one more time?
So the assumption behind the problem is that you need to add all of the streams.
Yes.
Rather than saying
sending one.
The 3 loudest streams, which in practice will probably be sufficient.
Yeah,
right?
yeah.
And so if you can select the relevant 3 encrypted schemes and then transform them so that an adversary doesn't know which ones they are.
I understand.
It's the similar problem to a mixnet.
Yeah. That's a solution. We haven't looked into that, but it's an interesting avenue for research. Okay. Yeah. I think Meta is doing something like this. I was talking to an engineer.
Hi. So have you looked into, because the way it looks like the problem is defined, into secure aggregation protocols for this?
Not yet.
Okay, so because it looks like all you're doing is just the addition of vectors, and it's a controlled environment in a way that I think parties can exchange some keys with each other. Yeah. So secure aggregation might be a sort of.
Yeah, it's an interesting pointer. Okay. But we would like to do more than just adding, but this is the first result we're showing and from the perspective of bandwidth, but yeah.
Okay, awesome, thank you.
Thanks.
In the beginning of the talk, you said that speaker anonymity is a desirable property, and I was wondering why.
So political question. We would like to have that, so there's no, some partners require that. I cannot discuss this further.
Okay.
We can
Thank
take
you.
this offline.
So it's quite interesting to add the voice of different people, but how about subtracting? So what about, see if I'm in a conference call with someone in the next door, I can record it and just inject the negative of his voice to the conference.
Yeah, we have results for that, but I couldn't fit it into the slides. So maybe next year, pre-over crypto, we did that. Very good observation.
Okay, let's thank our speaker again.
Thank you so much.